I'm Alex. I work at Monocle, which is working with e-commerce companies to help them better target their incentives, their coupons. And coincidentally, I'm going to be talking about building a user-level targeting platform. So, like, what are the odds of that? So, to motivate, to turn on the clicker. To turn on the clicker. There we go. All right, so suppose that you are an e-commerce brand and you are selling rubber ducks and you have these really cool Data Council rubber ducks and you want to grow your business, right? So you've got these ducks, they're selling reasonably well, but you kind of want to improve sales. And you've heard about coupons, right? So you've heard that, like, okay, I can increase growth by giving out some coupons. But I've also heard some horror stories of over-couponing, right? So I've heard of, I don't know if I want to name drop, but you know of brands that have over-couponed and have really hurt their value. And so you're kind of worried about that. So how should you choose a coupon strategy? And one way you could do this, which is actually there's option 0, which isn't on the slides, which is like you just choose something at random, which is what a lot of companies do. Don't do that. Option 1 is you could run an A/B test, right? So we could be data-driven about this, and we could say, okay, we have 3 different coupons that we could give. We could give, no coupon. I'll refer to that as like 0% off, 10% off, or 20% off, right? Just 3 different things. And we could do our standard A/B test, right? So you have your population, you randomly split them into 2 groups, or 3 groups, excuse me, and you give them the coupon, each group a different coupon, and you observe the results, right? And so here we're going to measure conversion, and we see that 20% off drives the most conversion. Surprise, surprise. And we're just going to say, great, let's ship that to everybody. And just to introduce a little notation that I'll kind of come back to, we can kind of talk about this as this E of Y given T, right? So if you're not familiar, E expectation operator just means like average of the thing, and then the bar conditional is like given that you got that treatment, right? So Y you can think of as outcomes that we would want to measure: conversion, revenue, profit, so on and so forth. T here is just the treatment, right? So which treatment they got. And so we can kind of refer to an A/B test as like measuring this expected value of Y given T. So we could do this, right? What's wrong with this? Well, first, we're assuming that what we observed in this A/B test, which is like the average effect, is going to be true for everybody, right? So we observed that giving 20% off was the best thing on average, but that doesn't mean that giving it to everybody is the best option, right? And it also is kind of a single point in time, right? So we ran this test, we analyzed the results, we ship it, we're done, right? There's no sense in which this could, behavior could change over time, and we'd want to measure that. So that's, one option. A better option, right, is to run a bandit, right? And so I think probably most people have heard of contextual bandits. You could use the data from that A/B test to train this contextual bandit. So now I've added an X in that expectation. So now I'm conditioning on some characteristics of each user, right? So now there's something about a user that will enter into this. And so here on the far side there, we can kind of think about 2 different types of users: the green user and the blue user, right? And they are going to have different treatment effects, or sorry, not treatment effects. Getting ahead of myself. They're going to have different effects, different predicted Ys from these things, right? So we can kind of talk about training this model to then generate these different predictions, right? If you're familiar with the bandit literature, they usually use R and A. We can talk about literature or how people name things later if you want. So you have this model, and then you need some way of kind of choosing the best option. Right here, it's kind of straightforward. You're just going to pick the best one. So the green user is going to get the 20% off, and the blue user is not going to get the 20% off. The best option for them is actually 10% off. Okay, and so then the model can kind of learn, the best thing. We generally, when we talk about bandits, we talk about balancing explore and exploit, or optimization and explore. which means that we don't always want to give the best thing because we want to kind of learn about the other options a little bit. If we always give the best thing, we're going to kind of lock ourselves into a potentially local maxima, and so we kind of want to keep exploring to make sure that that is actually a maxima. And I'll talk a little bit more about optimization in a little bit. And then the nice feature of the bandit is that because we're doing this exploration, we can kind of retrain the model over time. And so we have this kind of continually updating piece. We're not stuck in a single state of the world, and we can kind of learn over time. Okay, so this sounds great. And it is. I mean, bandits are great. I think a lot of people run bandits, and these are actually a really, really powerful tool. But I'm going to claim that there's something tricky about this. And the tricky piece is getting a good model of that expectation of y given t and x. Okay, and the reason this is tricky. So think back to our rubber duck example. Okay. There might be some characteristics, some x characteristics of users that are very predictive of y. And it doesn't matter at all what t you give them, right? So people in this conference probably more likely to want to buy a data council rubber duck than anybody else in the world, right? In fact, like everyone else would be like, what the hell is this? Why would I want this, right? And so it doesn't matter what coupon you give them, they're not going to buy it, right? And conversely, like here, maybe it doesn't matter. Maybe I don't need to give you 20% off. You're willing to buy at full price, right? Because it's cool, or not. But so I think in this case, right, you might have these kind of characteristics of the users that are going to dominate the effect of y. And so when you train this model, that's all that's going to get picked up, okay? And so therefore, when we fit a machine learning model to this, we are going to basically regularize away any effect of t. Right? And the t is the thing we care about, right? We want to pick the best t. And so I think that's where these cases where these models might not do a great job of actually getting to the thing that we care about, which is choosing between the coupons. Okay? And so what we really care about is a treatment effect. Okay? And it turns out there's a very, very large literature on estimating treatment effects. In fact, and kind of estimating heterogeneous treatment effects, which is what we'll talk about. So, shifting gears slightly, let's talk about heterogeneous treatment effect models. So here I'm going to say, let's just consider a binary treatment for now. So let's say, forget the 20% off, we're just going to talk about 10% and 0. And we're going to define this tau as the difference between two potential outcomes. The potential outcome where you get 10% and the potential outcome where you get 0. Now, the fundamental problem of causal inference is that you cannot observe that quantity. Okay? You can only observe one of those things. I can only give you a coupon or not a coupon at a single given point in time. I can't give you both, right? So that's why causal problems are hard, is you can't observe this. But it's the thing we actually care about, right? Is we actually want to know what would happen if we gave you a 10 compared to if we didn't. And so the whole point of these models is like, how do we go about estimating these expected value of tau given x? And so in the example here, right now we have this green user, we have the two things. It looks almost identical to what we saw before, except now instead of just leaving it at the levels, we're going to take the difference, right? So now we have the tau is defined as the difference between these two things. So if you're following along and you can do algebra in your head, which I can't, you can kind of go from this value, expected value of tau given x, to, and just properties of linearity of expectation operators, yada, 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 you can get down to this thing that looks a lot like what we saw before, right? Which is, in fact, you're just taking a difference between the two conditional expectations we had before. And so you're like, Alex, what the heck are you talking about? You just told me that this wasn't a good model. And you're right. So I think the simplest HG model we can write down is to say, just fit what we had before and take a difference. Okay, that is the simplest HG model. And that's what a lot of people do. So there's the S learner, which stands for single learner, which is literally just fit a single model on that, and you just have the T be a feature. The T learner, which is just fit two different models for those things and then take the difference. And so that you can do that, that's great. But what I would want to argue, and the literature has basically shown is that in a lot of cases, you can do a lot better than that. For exactly the reasons I mentioned before, there are, you're going to if in many cases you're going to regularize away the effect that you care about. You're not really explicitly going after the quantity that you care about. You're taking the difference afterwards, and that's not great. And so we can do better. But the challenge here is that almost all of this literature refers to this binary treatment, right? And so potential outcomes are defined as a difference between two things. But we had 3 treatments, right? We had 0, 10, and 20. How can we handle that? And so this, I think, is where, I will preface with, there needs to be more research here. But I think one way of conceptualizing this is to kind of think about this as a difference between a coupon and no coupon. So here we basically have 0% off and I think I call it Z% off. And so that's the kind of treatment effect we're going to measure, is between 0 and Z. And then we're going to kind of parameterize Z as the different values of a treatment, right? So here 10 and 20. And then that's going to give us that same picture we saw before, which is basically we can read off these different values of conversion, and we can then construct the taus that we want, right? Which is tau, now parameterized by the Z value, tau 10 and tau 20. Now, we have to be careful about this because it's not as simple as just taking that Z and throwing it in the model as another X, right? It's not just a user characteristic. And the reason that's not the characteristic, so the idea behind that conditional expectation, right, is we want to know for a given user who looks like X, right, what is their treatment effect, right? So we want to find comparable users who both got the treatment and didn't get the treatment, and then that's what we're going to use to kind of train that model. If all of a sudden we're going to add in a feature that is the value of the coupon they got, well, now you're never going to have a comparable user, right? You're never going to have a person that had Z equals 10 in your control group, because it's fundamentally that's the definition of the treatment. And so you have to be really careful about how you actually set this up. So one solution is a neural net, because neural nets can do anything. And so that works for this, is you can kind of write down this model in a nice network, and you can do it. The problem is that they really don't work well with limited data. And as Sean knows, we spent some time at Lyft trying to do this with neural nets, and really had some challenges there. Yeah, I wasn't blaming you, but it really was your fault. So another option here is Bayesian trees. So BART is a really good model, and I think there is a way to extend it, but it's kind of annoying to implement. Would love for more research from the people who are familiar with BART on this. So I think that's kind of the extension. So I think this is the way that, or at least the way we're thinking about how to extend this, so that we can talk about giving different treatments, learning what the best one is. So then I think coming back, is this all worth it, right? So I kind of just explained that there's some challenges here, you got to fit some extra models, there's more complexity. Is this actually worth doing? Everyone knows bandits are great. Should we be just doing bandits? And I think what I would like to try to convince you of is that there are cases where bandits are going to work fine, and there are cases where maybe this isn't they're not as good as you think they are. And so I think that there's kind of an important distinction between incentives or kind of other monetary things, and maybe messaging or kind of app design or things of that nature where you might have seen bandits run before. And I think the big thing is dollars, and kind of these trade-offs between dollars and between growth, if you will. And the other one I think is less important, but I think is kind of an interesting case here, is when we're talking about making that causal distinction of coupon versus no coupon, we're putting a lot of weight on this important baseline of no coupon, and then we're going to parameterize the different coupons. And so I think it does become a little bit interesting if you don't have a clear baseline treatment. it becomes a little bit like maybe this isn't the right framework. But I think in many cases, certainly in coupons, there's a obvious baseline treatment. I think in other cases, you kind of have a clear baseline that you could use for that. And then, so talking about dollars and trade-offs, so here I have just kind of a maybe not that useful chart of different outcomes that we might be interested in. So we have conversion, we have net revenue, which is just like gross revenue minus the cost of the coupon, gross profit, which is adding additional costs, LTV, what does that mean? And brand dilution, really, what does that mean? So I think the point of this slide is mostly that I'm kind of ranking the different coupons by, with completely and utterly made up numbers, by which is better. And there's not a clear winner, right? So if you only care about conversion, right, then okay, cool. Like always give the biggest thing. Like we're done. Like this talk is over. But I think like in most cases that's not true. We don't just care about conversion. We have some other things that we care about, and so we have some cost dimension that we're going to be interested in. And so we start talking about net revenue. We start talking about profit, and then maybe it becomes a little bit like we're trading off between these things. And then I think getting a good estimate of those treatment effects becomes very important, right? If it's always just give the biggest thing, like, okay, cool, maybe you can just use a simple model to do that. But if you're kind of trying to tease out the nuance of when break even is, when payback is, then maybe you need a slightly more causal model to get at. Cool. So putting this all together, what would this actually look like as a platform, right? So we can kind of run this initial experiment, right? So we randomly allocate this. That gives us the data to then train an initial HT model. We do that, and we can use that to then optimize. These slides are out of date. Anyways, I think I changed these last night, but that's okay. So we can optimize. I said with bandits, but that's I think misleading. Anyways, and then retrain the model based on that, right? So basically, we're using that initial model, doing some kind of optimization, which we'll talk about in just a second, to send the coupons, and then we're going to read off the response from those coupons to then retrain the model. And so this is basically, this is a kind of standard contextual bandit kind of thing, except we're replacing the kind of simple model for a normal contextual bandit with these HT models. So let's talk about optimization. So in general, like we can be pretty flexible about what the objective function is, right? So I listed a few different outcomes that we could talk about, but I think even within there, you can think about, it doesn't just have to be a simple maximization of things. You could talk about constrained maximization. You can talk about basically like whatever you can write down and potentially operationalize. You can do, which I think is one of the nice things about this is like you can kind of be very flexible about what inputs are going into the system. And then one of the kind of cool things is we can kind of use Thompson sampling, which is usually what people think about when they're talking about contextual bandits, not always. And so what that looks like is this picture on the right. So imagine that these are the three different coupons. So we have blue, red, and green. And this is like the distribution of predictions for a given user, right? So I basically have some uncertainty over what's going to happen if I give them each of these possible options. More right is better. And so if you ignore the uncertainty and you just take the best thing, you're always going to give blue, right? Blue is just like, if you look at it like the mean, if you just take the mean of that, like always give blue. But we can basically say, okay, we know that there's some uncertainty, or we can posit there's some uncertainty around these things. And we can take draws from that uncertainty, and then we can take the best thing from those draws. And so here, right, like the red distribution kind of covers more of the area. So we might draw from the red reasonably often. Occasionally we might draw from the green, right, where it's like, it just happens to be a little bit better, but like very likely we will not do the green because we think it's significantly worse, but we're still going to be exploring. And so that's basically what Thompson sampling is doing, right? Is it's basically just taking these draws from these distributions and picking the best thing, right? Or subject to whatever your optimization is. So the important point here is we need a model that can handle this. So we are now, in the previous slide, I think I had, we kind of start with this initial experiment, right, where we have a random A/B test, and we're going to train the model on that. And so generally, causal models like random data. And so, we might have the case where we just do, we have a model that can only handle random data. In order to do this kind of Thompson sampling thing, we need to have a model that can handle not completely random data. Okay, so that's not observational data, because we're still going to have some randomness from the Thompson sampling, right? We're going to add some uncertainty to these draws, but we do need a model that can kind of handle the fact that it's not always going to be, purely 1 over k of these things. And so I think that's an important context. So more complexity to the set of models that you can actually use to do this. So just a kind of quick grab bag of things. I don't really want to go too deep on any of these, but a couple cool things you can do. One, adding a new coupon. If you've parameterized this z, right, I can then say, I've never given a 30% off coupon, but I can generate predictions for what a 30% off coupon will look like, because I have a model that's parameterized by that. And so then you can kind of cold start a new treatment. And so you can basically say, that I can now, without ever having to run any kind of exploration on this, I can kind of generate predictions for this and send it out in the wild. Now, it depends on how good your model is at extrapolating, whether this is going to be wise or not. But I think with Thompson sampling, you could imagine that you're taking whatever predictions you get from the model and then putting like very wide uncertainty over it, and then you'll start exploring it and start shrinking that uncertainty. So that's a really cool piece of this. This isn't cool, but is, I think, a call to action on model evaluation. So evaluating causal models is hard. Evaluating heterogeneous causal models is even harder. And the current methods just suck for small data or small-ish data. So I think that's something I've struggled with a lot, and I think is something that I would love to see more research on is how do we actually do this kind of thing, because it's not easy. Long-term effects, I kind of joked about LTV earlier. I think this is something that generally we do see trade-offs between short-term and long-term effects. So a lot of this stuff on coupons is okay, we're gonna have this short-term jolt where we're gonna drive some short-term conversion, but really we're just gonna get a bunch of low LTV users, and then that's gonna be really bad. So I think that kind of trade-off, which I think is in the back of at least e-commerce minds, is really important. And so kind of if we can model that would be really good, and that fits nicely as an outcome. You just need a way of actually modeling LTV, which is a separate hard problem. I've kind of glossed over a single campaign of this. So kind of thinking campaign meaning just a way of allocating coupons, but there might be many, right? If you're running some e-commerce, you might have different flows. There's the first time you see someone, if they abandon their cart, if they've, been on the site and they bought 6 months ago, maybe you want to try and get them back. All of those different things, you could imagine having some kind of campaign. And so how can we learn, how can we do cross-learning from that in this case? I think is kind of a really interesting problem. And then I think similarly, cold starting a new campaign. So can we not run that first initial experiment, right? That's expensive to run an experiment initially. How can we kind of use some of that previous information to do that? Yeah, and so then kind of putting this all together, you could imagine that, this is very similar to the picture we had before, except now we're basically adding, kind of some kind of front-end dashboard to say okay, we can kind of set up that initial campaign or whatever. We can choose the inputs, we can choose the objective function, we can choose what constraints we want to do, train that initial model. That will start the optimization path, right? Maybe initially we're going to be really uncertain about all of these things, so we're just going to have these really wide overlapping bands, but we will slowly, as we start to send these things, learn more about how people are going to respond to these, and we'll start to tighten up those and get better and better about the optimization. That's the feedback loop into the model. And then the feedback loop into the dashboard is basically we can start presenting on results and show that this is working or it's not, and you need to update your inputs or your constraints. And so maybe if you do this really well, you'll show up and you'll go on Wirecutter and you'll see that this is really the very best rubber ducky in the world. Yeah. Oh, and then did I add one more? I did not add one more because they're not updated. I had a shameless plug for one. If you're interested in this kind of thing. No, it's fine. That's fine. It's really not important. It's really not important. I just had a picture of our website. So if you're interested in this, I work at a startup that's doing some of this kind of stuff. I would love to chat more about that.